Hi, I'm Anand. I've been a Python programmer for the last 15 years and a movie addict for about twice as long. This video is about me combining both of those interests. One thing that I've always been curious about is what it takes for two actors to connect with each other, and are there clusters of actors who tend to act mostly with each other? And that's what we'll be exploring now. Let's look at what it takes for one actor to connect to another actor. If they can only connect to their co stars, that is, people they have acted with in other films, then how can one actor connect to another? To do this, we're going to be using data from the Internet Movie Database, which is perhaps one of the most comprehensive data sets and collections of movies and actors. The Internet Movie Database provides a collection of data sets that are licensed for non commercial use and can be downloaded from datasets.imdbws.com. These are a collection of files beginning with the list of actors, the titles, alternate names, basic details of the titles, and so on. And each one of these has some very interesting information. What we'll be looking at specifically is a subset of these files. We look at title.basics.tsv.gz. Now, this is a gzip file that contains data in a tab separated value format, which is kind of like values separated by commas, except instead of commas, it's separated by tabs. Title.basics contains the basic information about the title ID, the title name, and so on. And the second file we'll be looking at is title.principles. This shares which title or which film has which actors. And thirdly, name.basics, which contains more details about the person, such as their name, year of birth, etc. To give you a feel for what these files look like, name.basics has the following information: a constant, a unique ID for the name, such as NM0000001, which stands for Fred Astaire, who was born in 1899 and was an actor and into soundtrack and others, and is known for these titles. These title IDs are available in title.basics.tsv.gz. You can access any one of these movies and actors by typing out the full IMDb URL. So if I copy this and look for, well, let's copy it from here and look for Fred Astaire, I can say imdb.com/name/ well, NM00000001. That will take me to Fred Astaire's page. Here we go. And if I instead typed in a title, it would similarly take me to a title page. The second is title.basics, which has the following information. Each row is a title. It may be a film, but it could also be a short film. It could also be a TV series. That's what title type contains. It also has information about the title name, which is called primary title, and original title in case if it was different in a different language, whether it's adult or not, the year in which it was started, which is often also the end year, or well, the end year is missing, but if it's a TV series that ran for multiple years, then the end year could be different. \n indicates that the data is not applicable. Runtime minutes is the number of minutes for this title, and the genres has comma separated values of the list of genres that the title belongs to. Title.principles has the following information. For each title ID, that is, for example, TT 000001, which is Carmen Cheetah, it has an ordering, which is just for each title, the cast order 1, 2, 3, and the cast. So this is NM1588970, which is some person, actor. Let's take a quick look at who this could be. It's a little hard to copy this and place that here. That happens, okay, to be the person, Carmen Cheetah. And she's acted in a film about herself or a title about herself, and there's no job description for her. The category that she's listed under is self, and the character that she plays is self. In this, there is also a different person, a director of cinematography, and a different person as a director. These are the others that are the cast in this particular film. Let's take a quick look at the cast. This has, okay, director William Dixon, That's the person we had seen, and somewhere we'd probably see a cinematographer as well as part of the cast of this film. Now, what we want to do is firstly get all the title details for movies, not for shorts or TV series. And within that, only look at where the category is actor, because we are saying it should only be the co-stars who we want to connect with, and then see how this network spans. You don't have to limit yourself only to movies. You don't have to limit yourself only to categories actors, but that's what we're going to do in this particular session. Let's now actually download the data. I'm going to use curl for this, but you could use any way you want to download the files. We want name.basics, we want title.principles and title.basics, and save them locally as .tsv.gz files. A few points here to make things faster. I'm using a -c- on curl. And what this does is, if the file hasn't already been downloaded, it will download it. If the file has been partially downloaded, it will continue. And if the file has been fully downloaded, it won't do anything further. Finally, we list all the files, and I have downloaded name.basics, title.basics, and title.principles.tsv.gz. Once we've downloaded the data, the next step is to load these. But there is a bit of a problem. At least if we use Python to do this, there is a bug. And this bug is specifically in Python's gzip modules. It turns out that a gzip file can have some trailing content, and this is ignored by gzip. But Python's gzip file module does not accept that, and it actually reports an error saying it's a bad gzip file. So a way to avoid this is to actually use the zlib module. Zlib.decompress can decompress gzip files as well, but without the same problem. So what we're going to do is use zlib instead and bypass the gzip module. But the main workhorse for reading the data is pandas, and we're going to be using pandas' read CSV function. What we'll do is create a wrapper around this read CSV function called read CSV, which will take exactly the same arguments that read CSV does, but instead of using pandas' default approach, which is using gzip to unzip the files, we'll effectively read the file, uncompress it or decompress it using zlib, and use that stream to pass to pandas and get the result. In other words, wherever you see read CSV, you could have used pd or pandas.readcsv, but the only difference is that internally we're using zlib to decompress. Let's actually load the data. First, we'll start with title.basics. This is passed the following parameters. The separator is a tab. CSV file expects a comma as a separator by default, but you can instead say it's tab delimited, and the TSV files, because they are TSV, tab separated values, you have to put in \t. You also saw that the missing values were characterized by \n. We use // to escape the \. The types for each of these we specify explicitly, and this speeds things up and reduces the memory usage. The fields that we are interested in are tconst, which is a string. That's the title ID, TT, some number. The title type, which could be a short or a movie, etc. The primary title, which is the name of the film, and the start year, which is an integer. And this is the data that we are going to be loading. I actually used int64 because int64 is a pandas data type that allows for integers, but also accepts nan or missing values. And we will have missing values where the start year for a film is just not known. Finally, we say the only columns that we want are these four: the title ID, the title type, the primary title, which is the title name, the start year. And we also set the index to tconst so that we'll be able to refer to it by this ID. To give you a feel for what the output looks like, this is the tconst as an index. We'll have the primary title and we'll have the year. But what I'm also doing here is only considering movies, not TV series. So we'll take movies where the title type is movie and filter based on that. Now that we've done this, we only have the movies, and that actually shrinks the data to roughly 1/20th of the original size, about 5%, and delete the title type because it's only ever going to be movie for this data set. So that's what our movies variable or movies data set looks like: an ID, a title, and a start year. The next data set we're going to read is title.principles. This has the following information: title ID, a name ID, that is the actor, and a category, all three of which are strings. There are other pieces of information, but these are the only columns that we're going to use. And again, it's going to be tab delimited with \n as representative of missing values. So this will ultimately give us the cast of each of the films. Now, given this, we only want to consider actors, not directors, composers, music directors, etc. That reduces the data to roughly about 40% of the original. And we also only want to consider actors that have acted in movies, not in the TV series or shorts or any of those. To do that, what we'll do is take the cast category, the category column, that must either be an actor or actress, and the cast tconst, which is the title ID that we have here, must be in the index of movies that we already have. And keep in mind that these exclude shorts and TV series. We filter based on that. So now cast has only the details about actors and actresses in movies. We then remove the index, which is what we see on the left hand side. We no longer need it. And then run the first 5 rows. This is what it looks like. It says in this particular title, this particular actor was an actor. In this title, this particular actor was actually an actress, and so on. Thirdly, we now need details about who these people are. So we're going to read name.basics.tsv.gz with a tab delimitation and a new line. And the columns we're going to read are nconst, which is the name of the actor, the primary name, which is their name. Well, sorry, nconst was the ID, primary name was the name, and birth year, which is a number, but it may be missing, so we'll use int64, and set the index to nconst. It roughly looks like this. We have the name ID, the name Fred Astaire, who was born in 1899. There's another item, titles, which we'll come to in a bit. First, we'll drop anyone who has not acted in movies. So we check if the name's index, which is this constant, is there in the list, in the cast list. If they aren't the cast of any movie, then we drop it. Second, we look to create a new column called titles. This is the number of titles or films that they or movies that they've acted in. And we calculate that by looking at the cast of nconst and then counting the values. So for each ID, let's say NM 000001 for Fred Astaire, it'll count the number of films that they've been a cast in. And that is 35 for Fred Astaire, and for Lauren Bacall, it's 37, and so on. That's what the third data set looks like. With this, we now have all of the pieces of information required for us to be able to draw connections between people. To find the shortest path between two people, we're going to be using a library called networkx. If you already have networkx installed, you should be able to say import networkx. If you don't, then you can pip install networkx. We're going to be using the abbreviation nx to import networkx. The next thing we're going to do is create a graph. A graph is an in-memory representation of all of the connections between the actors and the movies. We're specifically going to use a function called fromEdgeList. What this does is takes a pandas data frame that contains an edge list and converts a graph. Now, what's an edge list? It has 2 columns of node names. Now, let's talk about this. Nodes are basically things. You can have a node as an actor. You can have a node as a title. And what we have here is a collection of actors and titles that are connected to each other. And when there's a connection, we call that an edge. It's like a line between 2 things. When you look at the cast data set, it effectively draws a line implicitly between every movie and every actor. That is an edge. And this list of edges is what's called an edge list. So we're going to take cast as the edge list and say that we want to take the tconst column and the nconst column as the ones that define the nodes of the edges. From this, create a node. Now, when we have this graph can be used by networkx to do all kinds of interesting calculations. For example, we can find the shortest path between any 2 actors. Let's take Robin Williams as an example. Robin Williams is at NM 000245. And let's also take Angelina Jolie, who is at 001401. And see what are the ways in which these 2 actors might connect to each other if they were only connecting through co-stars. networkx has a function called shortest path, which takes a graph and the names of any two nodes. So we pass Robin Williams and we pass Angelina Jolie, and it gives us a result. It says NM 40245, that's Robin Williams, has acted in this film in which Angelina, oh no, sorry, this is someone else. I don't know who this is. In which, let's find out who this is. That's Ethan Hawke. So there's a film which Ethan Hawke and Robin Williams have acted together in, which happens to be titled Dead Poets Society. Great. So in Dead Poets Society, both of these actors have acted. And it turns out that Ethan Hawke has acted with Angelina Jolie in the film Taking Lives. So that's one path of connection, which is Robin Williams has acted in Dead Poets Society with Ethan Hawke, who's acted in Taking Lives with Angelina Jolie. Now, that was a little hard to read with just these numbers. So maybe we'll do something. We'll write a function that can convert these IDs to names. The function names does exactly that. What it does is returns a hyphenated string that joins whenever we are given a path. When I say a path, I mean an array like this. It creates a hyphenated string that returns all of these converted into names. How do we convert them into names? Well, if we loop through each element in the path, let's call it P, then if that element starts with TT, then it's a title, otherwise it's a name. And if it's a title, then we can get the primary title column, that is the movie name, for that particular ID from the movie's dataset. Otherwise, it's a name, and we can get the primary name of the person from the name dataset for that particular person. So if I said names of this particular cell, then I effectively get the full result, which is Robin Williams acted in Dead Poets Society with Ethan Hawke, who acted in Taking Lives with Angelina Jolie. Now, it would be convenient, however, if instead of specifying shortest path of NM something or the other, if we could specify the names as well. So, for example, if we could just say path between Robin Williams to Angelina Jolie, that would be really cool. So to do that, we'll create a function called path, which takes a source actor name and a target actor name. And then we'll look up the primary name of the source in the name dataset, get the index. And it may be that there are multiple Robin Williams. In fact, there are multiple Robin Williams. What we'll do is take the very first Robin Williams. Why is this an acceptable idea? Well, you may notice that the smaller the number, roughly the more popular the actor, at least. While that's not a robust rule, it's a reasonably good rule. And we perhaps should be taking the actor that has acted in more titles. But for now, we're just using a simple rule of thumb to say take the very first one on that list for the source and the target, and then get the shortest path for that particular ID to this particular ID, and then convert it back into names. So if we say path of Robin Williams to Angelina Jolie, we find that Robin Williams, Dead Poets Society, Ethan Hawke, and Taking Lives, Angelina Jolie is just displayed directly. And we can see that Robin Williams therefore somehow needs to connect to Ethan Hawke. But is that Robin Williams' only option? Could there be other paths? Well, let's take a function called paths. Let's create one, which is the same as path, but instead of shortest path, it uses networkx's all shortest paths function, and then return the names for each of those paths. So if that's the case, then let's look at all the shortest paths between Robin Williams and Angelina Jolie. It turns out that Robin Williams could also connect to Robert De Niro. They acted together in Awakenings, and Robert De Niro has acted in 2 movies with Angelina Jolie, which is Shark Tale and The Good Shepherd. Ethan Hawke is an option, but there's only Dead Poets Society connecting him to Ethan Hawke and Taking Lives connecting Angelina to Ethan. Matt Damon's another option, with Good Will Hunting and The Good Shepherd being the connectors. Brittany Murphy with Happy Feet and Girl Interrupted. Now, with Dustin Hoffman, there are 3 films that Angelina has acted with: Kung Fu Panda, Kung Fu Panda 2, and Kung Fu Panda 3. But Robin Williams has acted only in one with Dustin Hoffman, which is Hook. David Duchovny is another option, and there are a few others as well that he could connect with. So Robin Williams has at least half a dozen co-stars through whom he could connect to Angelina Jolie. What we have now is the ability to take any two actors and figure out what is the path that connects them together. Let's explore the shortest path between actors further. Supposing the Iranian actor Shahab Hosseini wants to connect to Angelina Jolie. What are the options that he has, and what are the actors through whom he could connect? So it looks like there are four paths that Shahab has. One through Golshifteh Farahani, who has acted with Melville Poupu, the French actor, and who has acted with Angelina Jolie. A second option is instead through Irfan Khan, through the Song of Scorpions, who's acted in A Mighty Heart with Angelina. A second set of routes is his co-star in A Separation, Payman Moadi, who's acted along with Clive Owen and Morgan Freeman in Last Nights, both of who've acted in different movies with Angelina Jolie. So that's Shahab's path, and it turns out that he has to connect to two actors to get to Angelina. So there's a separation of 2 degrees, well, 3 degrees actually, 1, 2, and if we have to count one edge or the other. So Angelina is 3 steps away from Shahab Hosseini. What about Onur Tuna? Onur Tuna is a Turkish actor, and his distance from Angelina is actually quite high, but he has multiple routes. Let's take a look. Onur Tuna is connected via several paths, but the length of the path is 1, 2, 3, 4, and 5. So, in other words, Onur Tuna needs at least 4 actors who can connect to each other for him to reach Angelina Jolie. And that's a pretty tough route. But there are several options for him to pick and choose amongst to get there. Let's take another scenario. Robin Williams, arguably one of the more popular actors in Hollywood, and Jackie Chan, arguably the most popular actor in Chinese films. What does it take for them to connect, given that these are potentially two comedians who'd want perhaps to act with each other? So they're separated just by 2 degrees. Robin Williams has acted with Dustin Hoffman, who's acted with Jackie Chan, as well as with Max von Sydow and Owen Wilson. So these are the 3 actors, and Owen Wilson's probably a better option given that he's acted with Jackie Chan in a couple of films. One of the other most popular Asian actors is Rajnikant, and if he wanted to act with Jackie Chan, it turns out that there is a connection just of second degree through Winston Chow, who's acted with Rajnikant in one film and with Jackie Chan in another film. What about Clint Eastwood with Toshiro Mifune? Toshiro Mifune is the Japanese actor who acts in the precursor to Fistful of Dollars, which is Yojimbo. And Clint Eastwood shot to fame through A Fistful of Dollars, which was a remake of Toshiro Mifune's, well, one of his most popular films. Now, if they wanted to act together, then there are a couple of ways in which they could do that through 2 degrees of separation. Clint Eastwood has acted with Lee Marvin, who's acted with Toshiro Mifune, and so has James Garner. And these are the paths. By now, you've got a feel of how one can explore the connections between actors as a network. I'd strongly encourage you to try this out, play it around, and see which of your 2 favorite actors could connect together easily and how they can connect between them. Let's now look at clusters of actors. What I mean by a cluster is a group of actors who tend to act mostly with each other, but very rarely outside of that group. Now, to detect such clusters, we can use scikit-network as a library. It has a series of network clustering algorithms. On Colab, incidentally, you may need to restart your runtime after installing scikit-network through pip install scikit-network. That's because it requires a slightly different version of NumPy than what is installed by default. But before we dive into how exactly to use scikit-network, let's take a look at different clustering algorithms and get a feel for it. To show you how this works, I'm going to take 4 different networks. Supposing we have points 1, 2, 3, and 4. And these are connected. So 1 is connected to 2, 3 is connected to 4. This is one kind of network, and they're connected very tightly. So this, for example, could be an actor who's acted with this actor, let's say 9 times. This is another actor who's acted with this actor 9 times, but they haven't acted amongst each other. This is one network. Another network is where these 2 actors have acted with each other, these 2 pairs, but this actor has acted with this actor at least once. Another variation of the network is where these two actors have acted once, these two have acted once, but these two have acted together 9 times. Another variation is where these two actors have acted together 9 times, and this actor has acted with this actor once, and this actor has acted with this actor once. Now, if we applied a network clustering algorithm on these 4 networks, and we ask it to break it into 2 clusters, then let's see how different algorithms respond. That will give us a feel for what algorithm works and how well it works. So I've captured the same data into 4 different networks, calling it C909. That 909 is an indication that there's a connection between the first to the second of 9 films, 0 films, 9 films. So that's why it's 909. Similarly, this is 919. This is 191. And this is 911. And all of these are created as a CSR matrix, which is a sparse matrix that we import from SciPy. And this is the kind of data structure that we'll need to create for scikit-network to use the underlying data. Then what we'll do is use a series of different algorithms. One such algorithm is scikit-network.clustering.lowain. There are others like scikit-network.clustering.propagation clustering. There's k-means and a variety of others. This fit function is a wrapper. What it does is takes an algorithm and then it takes each of the 4 networks that we just drew and does an algo is basically whatever is the algorithm we've shared, dot fit transform and prints the results. So for Lowain, here's what the results look like. It says 0011. What that means is this belongs to cluster 0, this belongs to cluster 0, this belongs to cluster 1, this belongs to cluster 1. So 0011. Now let's draw that as a picture. So what it's doing for the first network is it's saying these two belong together. These two belong together, but it's a separate network, which makes perfect sense. For the second network, it says 0011 again. So these two form a cluster, these two form a cluster, but these two, even though they're connected by one film, they don't really form a cluster. That makes sense too. For the third one, it says all of them belong to the same cluster. It says this, and this, all of them belong to cluster 0. Okay, that is not unreasonable. And for the fourth one, it says again, these two form one cluster. That's reasonable. And these two are connected into one cluster, even though there's only one movie that's connected. Well, that's not particularly unreasonable. Yeah, maybe we could connect them. Maybe we could leave them apart. That's a subjective call. So overall, Lowain seems to be giving us results that are reasonable, not necessarily ideal, but it's a subjective opinion as to whether these results are right or wrong. Let's look at how propagation clustering does it. In this case, it says these two form one cluster, these two form a different cluster. Makes sense. But beyond that, it says they are all a single cluster. It almost feels as if propagation clustering says if they're connected, I'm going to create a cluster out of it. Well, that's not exactly what we want for our actors. So we won't be using propagation clustering for our algorithm. Let's look at k-means. K-means says these two form a cluster, this belongs to that cluster, and this one's separate. Okay, that makes no sense. Then it says these two form a cluster when they're not even connected, and these two form a cluster. In fact, k-means clustering seems to give such bizarre results that I have a feeling I'm doing something wrong, but it certainly is not something that we are going to be using for our clustering algorithms. This apart, there are hierarchical clustering algorithms also. And we get those using scikit-network.hierarchy. One of them is called Paris. The way it creates a structure is these two form distinct clusters. That's reasonable. Again, these two form distinct clusters, even though there's one movie connecting them. That's fine too. But this is weird. It's saying even though this and this are very tightly connected, it's putting them in separate clusters. That's not ideal. This one seems fine. Let's look at Lowain hierarchy. That too produces reasonably intuitive results. This was the same as before. This is the same as before. This again makes sense. Out here it's saying these two are connected, but it would put this into this cluster, but not this. Okay, maybe it's not clear why, but fair enough. WAD is the last hierarchical cluster, And like with k-means, I wasn't able to make sense out of this. Why would these two not be connected, but these two are connected? Why would these two be connected when there is no linkage? So some of these weren't entirely clear. Overall, it seemed to me that the Louvain clustering, not the hierarchical one, but just plain Louvain, was A, certainly reasonable, but also among the most popular clustering algorithms. So that's the algorithm that we're going to be using to cluster the actors. The first thing we need for the clustering algorithm to work is an adjacency matrix. That is, a matrix that has the actors who have acted with each other connected via an edge. So what we'll start with is first an adjacency matrix of actors to movies and then convert it to actors to actors. How do we do that? Well, what we need is a matrix where each row is one movie and each column is an actor, and the cell should be 1 if the actor acted in the movie. Otherwise, it should be 0. Now, to convert this or to get this out of the data set, we primarily need the cast data set. And you might remember that cast has a column called tconst, which is the ID of the movie, the title, and an nconst, which is the ID of the name, which is effectively the actor. And this is what has to be converted into a matrix where this, if let's say the third tconst is acting with the seventh nconst, then cell 3 comma 7 should be 1. Let's do that. Now, what we'll do is use pandas category data type to do that. I'll take tconst and convert it to a category, assign it to title, and similarly nconst and assign it to a name as a column in this cast data set itself. The reason this helps is because these category column types, they have an attribute called .cat from which we can take .codes and .values. And that is kind of like a zero indexed ID or the equivalent of a row number and a column number. So what it does is automatically assigns unique IDs to each of the tconsts and the nconsts, and we can get those IDs from this particular expression. So we'll assign that to row and column. What that now gives us is a data frame where the first 5 rows have a statement that says, in our big actor movie matrix, the 0th row, 44,206th column should be marked as 1. Similarly, 0th row, 50,861st column should be marked as 1, and so on. This is something that we can convert into a matrix. We'll be using a sparse matrix. The reason is there's a huge number of actors, a huge number of movies, and 99.9% of the values are going to be 0. We actually only want to fill in the ones, and the rest can be treated as zeros. So the way we'll do that is by using SciPy's CSR matrix, which is a column sparse matrix. And it takes 3 parameters. Well, 2 parameters actually. The first is the data set itself that has the values that we want to put in here. Now, the only values that we want to put in here are ones. We want to put in as many ones as there are data in our list here. And then another, which is a pair of rows and column IDs. So we basically say take the row, take the column, and the data itself is just ones. So this is what it looks like. So if I print the first 10 rows from columns 44,200 to 44,210, which is where we expect to see a 1 against 44,206, we see that in row 0, that is the actor indicated by this particular, the title indicated by this particular row, has a 1 against 44,206, which is basically saying that this particular actor has acted, this particular title has this particular actor. Now we have our matrix. Let's convert this movie actor matrix into an actor-actor matrix. Specifically, what we want is each row is an actor, each column is also an actor, and the cells should show whether, in fact, how many movies they've acted together in. So if they've acted together in 10 movies, that cell should be 10. If they've not acted together, it should be 0. The way we do that is simply by squaring the matrix. We transpose this matrix multiplied by itself, and that gives us the squared matrix. I'm not going to explain how and why this works, but this is in fact one of the most powerful things about matrix algebra, that it just works. And for network analysis, if you're able to figure out this part of it, then well, you'll have a lot of fun. And then we set the diagonal to 0. So if we actually take the matrix, it'll show that each actor has acted with themselves several times. If they've acted in one film, they've certainly acted with themselves at least once. Now, we don't really care about people acting with themselves. So we'll set the diagonal to 0. So now this is what it looks like. This effectively says that actor number 1 has acted with actor number 6 once, and with actor number 7 4 times. Actor number 6 has acted with actor number 1, that is 0 1, yeah, at least once, and so on. And this you'll see is a mirror image along the diagonal. The 1 you see is the same as the 1 here. The 4 you see is the same as the 4 here, because if A has acted with B 4 times, then B has also acted with A 4 times. Now what we need to do is convert this into a data frame so that we can start reading the actual IDs. But I'm not going to show you how to do that. All of that is wrapped into a function called getPairs, where the code to actually reindex it is out here. But when you see the result of this, you finally get a data frame that says that this actor and this actor have acted together 187 times. This actor and this actor have acted together 187 times. That's literally just the reverse of this pair. And then these two actors have acted 146 times together. Another pair have acted 130 times together, and so on. It would actually be nice to have the names of these actors so that we can explore. Now, it's possible for us to manually look up some of these, such as IMDb/name/this ID. And that tells us that one of the actors is Bahadur. But it's going to be easier for us to write a lookup function that does that. Again, I'm not going to go into the lookup function, but here's what the result looks like. The Indian Malayalam actor Bahadur has acted with Adur Bhasi, a co-star, as many as 187 times. The Japanese actor Kijaku Otani has acted with Matsunosuke Ono over 140 times, and so on. This is the starting point of us being able to build the network and applying the clustering algorithm. You now have all of the information required to create a worldwide cluster of actors. 1, how to create the adjacency matrix, and 2, how to actually go about using Louvain as an algorithm to create the cluster. I'm not going to go step by step through the rest of the functions in this code, but just give you a cursory overview over the next few minutes so that you can get a feel for what is possible with this. One of the utilities that I built is to tag actors. Once we have an actor, let's say like Adur Basi or Bahadur or Kijaku Otani, how do we know which cluster they belong to? Can we give names to these clusters? So what tag actor tags does is for different actors, let's say Amar Waked, tag them as Egyptian, or take Anjali Devi, tag them as an Indian actor, also as a South Indian, also as Telugu, also as old. And Ansa Ikonen, tag them as Finnish, also as old. So we provide multiple tags for each actor so that if there are actors that belong to multiple clusters come together, then no matter how they come together, we can still give the cluster a name. The other utility that we have is the actual clustering, which creates the clusters by building an adjacency matrix and then uses the Louvain algorithm to create the cluster, and then finally uses the actor tags to name the clusters. Finally, we also add a set of cluster metrics here, such as how large the cluster is, how many co-stars each person has, and so on. Let's take a look at what the output of this particular function is. If we call the subcluster function in this notebook, it reports for each actor, apart from their basic details such as birth year and the number of movies they've acted in, the cluster number that they belong to. So Adur Basi and Bahadur belong to the same cluster. Kijaku Otani and Matsunosuke Ono belong to the same cluster, and so on. And it also gives a name for these clusters. Sometimes the cluster may have multiple names. So this looks like the Indian, South Indian, Old, Tamil, Telugu, Malayalam cluster. This is just having one name, the Japanese cluster, and so on. We also get information about, for each actor, how many unique co-stars they have, how many clusters they act together with. So Kijaku Otani has acted in only one cluster, the Japanese cluster, but Bahadur has acted with two clusters, his own and one other, and Adur Basi has acted with two clusters outside of his own. How many pairings they have, that is the total number of co-starrings, not just unique co-stars, but total number of co-starrings they've had, and what percentage of those were within the same cluster. So 99.4% of Adur Basi's co-stars or co-starrings were within the same cluster that he belongs to, and 100% of Kijaku Otani's were Japanese co-stars. Now, this kind of a network information allows us to create something more powerful. What we can start looking at is not just the network of actors, but the network of clusters themselves. That is, how can the clusters themselves interact together? This visualization shows the top 30 actor clusters in the world, with Hollywood being the largest cluster and the cluster of Spanish Mexican actors being the second largest, and so on. Now we can start looking at how actors in Hollywood, or how often actors in Hollywood act together with British actors, with old American actors, with Spanish or Mexican actors, etc. The first connection is from British to Hollywood films. Hollywood actors act with British actors about 5% of the time. Hollywood television is not too far away. Hollywood horror films are fairly close to mainstream Hollywood as well. These actors tend to act with each other fairly common. Old French actors are well connected with Hollywood. The first non Hollywood cluster comes with the Japanese and the Japanese porn clusters coming together. It's interesting that Japanese porn is almost a separate cluster in itself, with all of these actors acting only within themselves and the Japanese mainstream actors acting only within themselves. There's also a Hollywood porn cluster, which is actually so distant from Hollywood that you'll find that it connects to Hollywood pretty late. We'll come to that. But this is the first independent cluster, that or network or pair of clusters that are connected outside of Hollywood. Italian, and now we have another cluster, North Indian and South Indian. Again, within the same country, but these clusters are so distinct that they form separate groups themselves, but they connect at about a 3.3% frequency. Then we have old American actors, which are interestingly more close to old French actors than with Hollywood. We have Italian actors, old German, and the overall Hollywood network keeps spreading. This keeps going on with most of West European and even East European, like Yugoslavian films, coming together to act with Hollywood. But you also saw that the Chinese and the South Korean films come together to form the first cluster that is truly cross-border as well as outside of Hollywood. And then we have other streams connecting. You'll see that Hollywood porn only just connects. So it's actually easier to be a Brazilian actor and act in Hollywood than to be a Hollywood porn actor and act with Hollywood. So at this point, we have the North Indian, South Indian cluster, the Japanese and Japanese porn cluster, the Chinese and the South Korean cluster, and the other industries, Indonesian, Greek, Filipino, Iranian, Egyptian, Turkish, they are still unconnected. They don't act with each other even 1% of the time. Let's keep going and see what connects next. Old French connects, Egyptian connects, but we still have Filipino, Indonesian, Turkish, and Iranian disconnected. Indonesians connect with the Chinese films about 0.5% of the time. The Turkish and the Iranian cluster forms, that's at 0.5% of the time, leaving Filipino cluster as the single most isolated cluster in all of the movie industry. In fact, even when the Chinese and Japanese films start connecting with mainstream Hollywood, and also the connections start forming between, let's go a little more. The Indian films start connecting with the British films. The Filipino cluster is still isolated, and the Iranian cluster connects with the Hollywood cluster, but the Filipino cluster is still isolated, making it absolutely by far the most disconnected cluster in the world. What I really hope to show you was the kind of insights that network analysis and network clustering can bring forth. By applying this on movie data, I hope it was both fun as well as educational. Do try it out. If you face any challenges while you implement this, then please add to the comment section and I'll help as best as I can.